Buenos días. La Universidad de Málaga se siente especialmente orgullosa de acoger este primer Congreso Internacional de Catálisis y Biorefinería. Y por ello, en nombre de la rectora, quiero daros la bienvenida a todos los asistentes, deseando que paséis unos días intensos y satisfactorios científicamente, además de muy gratos en relaciones sociales y actividades culturales en el marco de las acogedoras ciudades de Torremolinos y Málaga. Good morning. I would like to welcome all of you to the first International Conference on Catalysis and Biorefineries. Firstly, I would like to thank all of you for coming, and a special thanks to those that have traveled so far to be here today with us. It is my pleasure to introduce the President of the Organizing Committee, Mr. Manuel López Granados.
Good morning. Ms. Susana Cabrera, Director of the International Relationship Office of the University of Malaga. Eduardo Falabella, representative of Petrobras. Dear colleagues, it gives me an enormous pleasure to greet you all here this morning on behalf of the Organizing Committee at the opening of the Catbior Congress. I don't think I have to convince you that biomass processing in biorefineries will be essential for a sustainable development of our society. But we have to admit that biorefining is still in its infancy, and there are important challenges ahead. In the last 10 years, we have witnessed the extraordinary increase of the utilization of biofuels. The use of bioethanol and biodiesel is now a reality in many countries all over the world. This persistent annual growth rate of biofuels came also with new problems and threats. I can mention the competition with resources originally devoted to human food, low energy efficiency, an impact in the reduction of greenhouse gas emissions lower than expected, and threats in the economical and environmental sustainability of the biofuels industry. Nowadays, there is a wide consensus that the solution will probably require the utilization of new biomass feedstock, not in competition with human food, like lignocellulose, for example, or microalgae or non-edible oils, and also the integrated transformation of biomass in new biorefineries to produce not only biofuels but also bio-based products, energy, and why not also food. The investigation in new technologies to optimize the integrated processing of biomass is currently very intense. Catalysis will be in a central position in the development of future biorefineries as it occurred in the past for the conventional petrochemical refineries. As a matter of fact, reputable scientific journals are already reporting the progress in the catalytic processing of biomass, and new breakthroughs are rapidly taking place in the field. So a couple of years ago, we, the members of the organizing committee, decided to organize the first of a hopefully long series of Catbior congresses. We thought that a congress devoted only to catalytic technologies for biomass processing was needed. A congress is an excellent opportunity in which researchers from industry and academia gather together and can update, disseminate, and closely debate new breakthroughs in the field. And also they can meet to each other and initiate new collaborations. So we stepped forward and decided to launch the call for the Catbior Congress. Now the day to start the Congress has come, and we are very glad that over 175 researchers from more than 30 different countries are attending the Congress. Countries overseas like USA, Canada, Brazil, Argentina, Chile, Mexico, Colombia, and even as far as Thailand, Malaysia, China, Republic of Korea, Japan, and Australia are represented in Catbior. We are also glad that participants from several companies are also here among us, like Shell, Eni, and Petrobras, whose representative will give us a keynote lecture. We will have the opportunity to listen directly from them, their opinion and prospects about biorefining. This response from researchers from all over the world is a clear proof that this type of Congress is really needed. We hope that the Congress will be scientifically fruitful for all the participants. Please take part of the debates and make your opinion known. Finally, let me summarize to you the other side of the Congress, namely the social activities. This afternoon, we will have a guided visit to the historical district of Malaga and also to its cathedral. After this sightseeing tour, you are invited to have a casual dinner with a variety of Spanish tapas in Restaurante Mariano. Several buses will be available for the ride to Malaga and also for coming back. Tomorrow, we will have the Congress dinner at Restaurante El Mero at Puerto Marina Harbor in Benalmádena at a walk distance, around 15 minutes, more or less, from the Congress venue. Nonetheless, transportation by bus will be also provided. Welcome to Torremolinos, welcome to Malaga, and welcome to Catbior Congress. We hope that you have a wonderful time here among friends in these two renowned cities of the Costa del Sol, a frequent holiday destination for numerous foreign tourists due to its cultural and gastronomical offer and its first-rank hospitality. Thank you very much for your attention.
And now the Research Director of Petrobras, Dr. Sousa Aguilar, will address us.
Okay, good morning, everybody. Good morning, ladies and gentlemen. Good morning, my dear colleagues of the catalytic community. It is surely a pleasure, a privilege, an honor to be here representing Petrobras. On behalf of my company, Petrobras, I should like to say to you all that my company is no longer just an oil company. Petrobras is indeed much more than that. Petrobras is now an energy company. That is to say, Petrobras is very much concerned about the existence of biofuels, about the green stuff. Actually, Petrobras has launched not long ago, about 3 years ago, a new subsidiary called Petrobras Biofuels. This company is concerned not only with the production of first-generation biofuels, but also with research and development. Actually, Petrobras Biofuels is investing a considerable amount of money in research and development regarding biofuels and next-generation biofuels. Petrobras is really dealing with thermochemical routes, with lignocellulosic materials, with sucrochemistry, and more, last but not least, with oleochemistry. So, ça va sans dire, it's necessary to say that the importance of catalysis is enormous in all those chemical routes. In order to get the transformation of biomass into not only biofuels but added value products, we need catalysis. Catalysis is very important. The presence of catalysis is surely paramount, okay? So, again, thank you very much indeed. It's an honor, as I have already mentioned, to be here on behalf of Petrobras. And I should like to end my words, not with my own words, but with the words of the famous poet, South American poet, Pablo Neruda. He said once, "We shall sort it out completely. We shall obligate you, earth. We shall obligate you, sea, to perform miracles, because inside ourselves, in the daily struggle, is the fish, is the bread, is the miracle. Thank you very much indeed.
After these nice words, President of the Organizing Committee, Dr. Eduardo Falabella Sousa Aguilar, participants at the first International Conference on Catalysis for Biorefineries, it is a great pleasure and honor to be here representing the President of the University of Malaga at this conference. We value the work that will be done these days in this field through an intense program which focuses on the future, a future where most of the fuel will come from biomass. Nowadays, governments all over the world from different countries reaffirm the importance of the biofuels as means of not only energy independence, but also a way to create jobs. The catalysis is an open door to the future, a future with economic and social implications that will be marked by a rhythm that today depends on the science that you represent. This conference will provide great opportunities to exchange ideas and learn from colleagues from around the world. And I wish you every success for a productive and highly informative conference. In addition, for those of you visiting from outside of Malaga, I hope that you get a chance to enjoy many things that the town has to offer to you. As a representative of the President of the University of Malaga, I would like to again welcome all of you and declare that this conference to be officially open. Thank you very much.
Again, good morning, ladies and gentlemen. It's our pleasure to introduce the first speaker of this morning. And with no further ado, let me give you the title of this lecture, which is going to be Heterogeneous Catalysis for Glycerol Valorization. And please let my colleague introduce the speaker of this morning.
So, good morning, everybody. It's really a pleasure for me to be here today. And first, I would like to thank the organizer for this nice place. So, it's a pleasure for me to introduce Professor Keiichi Tomishige. Keiichi Tomishige received his PhD from the University of Tokyo, working with Professor Iwasawa. After being research associate, he moved to the University of Tsukuba as a lecturer and associate professor. And since 2010, he is professor at University of Tohoku. He get a Young Scientist Award of Japan Petroleum Institute in 2000 and Young Scientist Award of Catalysis Society of Japan in 2004. His research interests are on the development of heterogeneous catalysts for different fields, such as steam reforming of biomass tar, syngas production by natural gas reforming, direct synthesis from methanol and CO2, and from today, hydrogenolysis of biomass-derived chemicals. So today, as you say before, he will present his results on heterogeneous catalysis for glycerol valorization. So it's to you.
Thank you very much, Chairperson, for kind introduction. I'm Keiichi Tomishige from Tohoku University. At first, I would like to express my deep thanks to the organizing committee for inviting me and giving me the great opportunity to introduce our recent research results in this very important and interesting conference. Before starting my presentation, I would like to mention that one of the largest earthquakes with magnitude 9.0 attacked the Tohoku area in Japan on March 11th. This is a map of Japan. The center of the earthquake is here, and Sendai City and our university is here. Tokyo is here. Tohoku University School of Engineering is located on the top of Mount Aoba. The distance from the center of the earthquake is about 170 kilometers. And as you know, the serious nuclear accidents there in the Fukushima. Distance from the Fukushima Daiichi nuclear power plant is 100 kilometers. As you know, the tsunami also attacked the seaside of area Tohoku region. This is a photo of a giant tsunami coming here. And this is a photo of disaster waste. At present, the disaster wastes are removed and separated. Tohoku University is also in the affected area. Therefore, this is a photo of the landslide in our campus. And this is a photo of my laboratory. All the cylinder fell down like this. Here, we are appreciating the support and a lot of warm messages of encouragement from all over the world. Now we are managed to restart education and research, and we are approaching the normal state steadily. I would like to go back to my presentation. First, I would like to introduce the biomass-derived chemicals, glycerol, for example, glycerol and its conversion. Second is a catalyst for the glycerol hydrogenolysis to 1,2-propanediol. Third is glycerol hydrogenolysis to 1,3-propanediol using rhodium-rhenium and iridium-rhenium catalyst. Next topic is the application of a catalyst to other hydrogenolysis reactions. For example, hydrogenolysis of tetrahydrofluoryl alcohol to 1,5-pentadiol. Here, I would like to explain the structure of rhodium-rhenium, rhodium-molybdenum, iridium-rhenium catalyst. After that, I will propose a reaction mechanism, glycerol and THF hydrogenolysis. Last part is a conclusion and outlook. This slide shows the composition of the feedstock and target products, such as diols. This axis means the molar ratio of hydrogen to carbon, and this axis means the molar ratio of oxygen to carbon. Fossil fuels, fossil resources such as coal, petroleum, and natural gas are located here. Since the petroleum has very low oxygen content, therefore oxygen-containing chemicals, oxygenates, are produced by the oxidation with air. On the other hand, biomass-derived glucose, cellulose, hemicellulose, and glycerol has very high oxygen content. Therefore, the oxygenates are produced by reduction. Possible reducing agent is hydrogen. As you know, the glycerol is one of the most important building blocks in the biomass refinery. This is a scheme of the production of biodiesel fuel by transesterification of vegetable oil. Glycerol is a byproduct in this process. This figure shows the global projection estimates by P&G of glycerol production. The amount of glycerol production increased with increasing the production of the biodiesel fuel. Therefore, a lot of researches on the glycerol conversion have been done actively. There are various methods for glycerol conversion, such as oxidation, dehydration, carboxylation, gasification, esterification, and so on. My talk is focusing on the hydrogenolysis. This slide shows the reaction route of the glycerol hydrogenolysis. Hydrogenolysis means the dissociation of the CO bond and addition of hydrogen. Glycerol hydrogenolysis gives the 1,3 and 1,2-propanediols. And the consecutive hydrogenolysis of propanediols gives the 1 and 2 propanols. Degradation, cis-cracking reaction is a side reaction. The most variable product is 1,3-propanediol. For example, in order to get propanediol, high activity and selectivity of glycerol hydrogenolysis to 1,3-propanediol is needed. And at the same time, low activity of hydrogenolysis of 1,3-propanediol to 1-propanol is also needed. Second topic is the catalyst for glycerol hydrogenolysis to 1,2-propanediol. Glycerol hydrogenolysis 1,2-propanediol is not so difficult. This is because nickel, copper, ruthenium, rhodium, platinum catalysts gave 1,2-propanediol as a main product in hydrogenolysis. And at the same time, high yield of 1,2-propanediol was already achieved. For example, Professor Sato at the Chiba University of Japan, he reported that the 96% yield of 1,2-propanediol using the kappa catalyst. My first contribution for the glycerol conversion is the glycerol hydrogenolysis to 1,2-propanediol using the ruthenium carbon plus amberlist catalyst. The addition of amberlist to ruthenium carbon promoted the formation of the 1,2-propanediol drastically. This phenomenon is interpreted by the indirect dehydration plus hydrogenation mechanism. Glycerol is converted to acetol by dehydration by solid acidity of amberlist. Next, acetol is converted to 1,2-propanediols by hydrogenation over ruthenium carbon catalyst. During this research work, we found that the rhodium silica is an effective catalyst for the glycerol hydrogenolysis. Rhodium silica is more active and selective for the glycerol hydrogenolysis than ruthenium carbon. Rhodium silica gave higher selectivity to 1,2-propanediol and lower selectivity of degradation reaction carbon. As reported previously, two kinds of reaction mechanisms have been proposed. One is a dehydration plus hydrogenation mechanism, dehydration and hydrogenation. Second is a dehydrogenation plus hydrogenation mechanism. Dehydration, dehydrogenation, and hydrogenation. In both cases, the main product is 1,2-propanediol, and the consecutive reaction of 1,2-propanediol is very slow. An important point is that both mechanisms are indirect hydrogenolysis reaction route. I would like to move on to the third topic, glycerol hydrogenolysis to 1,3-propanediol using rhodium-rhenium and iridium-rhenium catalysts. 1,3-propanediol is more variable than 1,2-propanediol. But no catalyst systems gave 1,3-propanediol as a main product in the glycerol hydrogenolysis. And high yield of 1,3-propanediol has not been achieved. For glycerol hydrogenolysis to 1,3-propanediol is more challenging than that to 1,2-propanediols. There are various reports, several reports on the glycerol hydrogenolysis to 1,3-propanediol. These four catalysts are metal plus tungsten oxide. Although the details are not demonstrated, but these catalysts are regarded as metal plus acid bifunctional catalyst systems. In this case, 1,3-propanediol formation route of these bifunctional metal acid catalysts is indirect dehydration hydrogenation mechanism via 3-hydroxypropanol intermediate. A problem of this route is a loss of the intermediate due to the consecutive dehydration to acrylane. Our strategy is direct hydrogenolysis. For example, using the metal catalyst directly modified with metal oxide. Our finding is that it is modified with rhenium, catalyzed glycerol hydrogenolysis into 1,3-propanediol with 38% yield. It is characteristic that the iridium-rhenium silica has a very high turnover frequency even at lower reaction temperature. Here, I would like to explain the experimental method briefly. Catalysts were prepared by a sequential impregnation method, a conventional impregnation method. Catalytic reactions were carried out in an autoclave reactor. I used pure glycerol. And the hydrogen pressure is 8 megapascal, and reaction temperature is 393 Kelvin. Catalysts were characterized by XRF, STEM, and XRD, seaward absorption, and so on. I would like to show you that first, the additive effect of second metals to rhodium silica at this molar ratio. Bar graph represents the selectivity of the products. 1,3-propanediol, 1,2-propane-diol, 1-propanol, 2-propanol, and degradation products. And this mark is, means glycerol conversion. You can see that the rhenium and molybdenum are promising additives. This is a yield-based figure. 1,3-propanediol yields becomes 40 times by the rhenium modification. And the rhenium silica has no activity. Therefore, high activity of this catalyst is due to the synergy between the rhodium and rhenium. Data of the rhodium-rhenium silica catalyst are plotted in the relation, in this relation, conversion and 1,3-propanediol selectivity and 1,3-propanediol yield. Unfortunately, rhodium-rhenium silica is not a good catalyst for the glycerol hydrogenolysis to 1,3-propanediol. Much higher selectivity is required. Therefore, we tested the hydrogenolysis of glycerol of various metal and rhenium silica catalysts, such as iridium, rhodium, ruthenium, palladium, platinum, and palladium. You can see that iridium, rhenium silica gave the highest selectivity to 1,3-propane-diol. Next, I would like to try to investigate the effect of additives on iridium silica, such as rhenium, molybdenum, tungsten, vanadium, chrome, manganese, and silver. It is clear that rhenium addition to iridium silica was most effective. This is the result of the activity test. Iridium silica and rhenium silica showed no activity in the glycerol hydrogenolysis, but the iridium-rhenium silica showed high activity and selectivity, 1,3-propanediol selectivity. This indicates that the synergy between the iridium and rhenium generates the catalytic activity. This figure shows the conversion and 1,3-propanediol selectivity as a function of reaction time. An important point is that the selectivity to 1,3-propanediol at low conversion is about 70%. And the maximum yield of 1,3-propanediol was 38% after 36 hours here. The data of iridium-rhenium silica is also plotted in this relation, like this. It is clear that the higher 1,3-propane-diol yield is given by this catalyst. This slide shows that this table lists the hydrogenolysis of propane diols over iridium-rhenium and rhodium-rhenium catalyst. In the case of iridium-rhenium silica catalyst, the reactivity of 1,2-propane-diol is much higher than that of 1,3-propane-diol. This suggests that the iridium-rhenium silica recognizes the position of the OH group, which is connected to selective hydrogenolysis of glycerol to 1,3-propane-diols. In contrast, in the case of rhodium-rhenium catalyst, the reactivity of 1,2-propane-diol was almost the same as that of 1,3-propane-diol, which is connected to less selective catalyst. But the rhodium-rhenium silica catalyst showed very high activity Therefore, high activity of this catalyst is applied to other reactions, such as hydrogenolysis of tetrahydrofluoric alcohol. Next topic is the hydrogenolysis of tetrahydrofluoric alcohol 2,1,5-pentadiol. Tetrahydrofluoric alcohol is called as THFA shortly. As reviewed by Professor Marshall Schraff, THFA is derived from the hemicellulose by fluoride. And the problem of the hydrogenolysis of THFA is 2,1,5-pentadiol is no good catalyst. I would like to explain the hydrogenolysis of THFA. Hydrogenolysis of THFA can give three products. Green bond dissociation gives the 1,2-pentadiol. Red bond dissociation gives 1,5-pentadiol. Black one gives the 2-methyl tetrahydrofuran. Target product is the 1,5-pentadiol. Since the no good catalyst, the three-step process has been reported. The yield of three-step process, 1, 2, 3. And yield of 1,5-pentadiol in the three-step process is about 70%. Recently, we reported that these catalysts are effective to the hydrogenolysis of tetrahydrofluoric alcohol, hydrogenolysis of THFA to 1,5-pentadiol in a single step. And the highest yield of 1,5-pentadiol is 94%. At first, I would like to show the results of the effect of additives in hydrogenolysis of THFA over rhodium silica catalyst. Bar graph represents the production selectivity of the product. 1,5-pentadiol, 1,2-pentadiol, 1-pentanol, and 2-methyl tetrahydrofuran. And this mark represents the conversion, THFA conversion. You can see that the rhodium rhenium X and rhodium molybdenum showed very high activity. Another interesting point is that the main product of rhodium silica is 1,2-pentadiol. On the other hand, a main product of rhodium rhenium silica is 1,5-pentadiol. The selectivity of the hydrogenolysis was switched by rhenium addition. This slide shows the dependence of the added rhenium amount. The optimum amount of rhenium was 0.5 as a molar ratio. I would like to show the results of the hydrogenolysis of tetrahydrofuran, THF, without CH2OH group. In this reaction, rhodium rhenium silica has very low activity of THFA hydrogenolysis. The large difference suggests that the interaction between the rhenium X species and CH2OH group, interaction between the rhenium X and CH2OH group in THFA molecule enhance the catalytic activity. We also try to produce 1,6-hexanediol from the THPM hydrogenolysis. Rhodium rhenium silica and rhodium rhenium carbon showed high activity and selectivity, like this. The maximum yield is 84%. A topic of this THPM hydrogenolysis is presented in more details by Ms. Kayo Chan on Wednesday. This is a recent paper on the catalytic conversion of 5-HMF into caprolactam, reported by Netherlands group. They reported that the rhodium rhenium silica catalyst was effective to the one-pot conversion of THFDM to 1,6-hexanediol. I would like to summarize my talk up to now. On metals, rhodium and iridium modify with metal oxide, rhenium or molybdenum, catalyze the selective hydrogenolysis. This figure shows the hydrogenolysis activity and selectivity over these catalysts using these reactants. Hydrogenolysis activity order, this axis is a reaction rate. Hydrogenolysis activity order using various reactants tends to be similar. Highest is rhodium-rhenium, and the lowest is iridium-rhenium. An important point is the selectivity is strongly influenced by the reactants. We are thinking that the number of OH group, THFA is single OH group, 1,2-propanediol double OH group, glycerol is triple OH group. From iridium-radium is more selective. On the other hand, rhodium-molybdenum is less selective. I would like to move on to the rhodium-rhenium, rhodium-molybdenum, iridium-rhenium catalysts. First, I would like to show you that the effect of additive amount of in THFA hydrogenolysis. In the case of rhodium-rhenium catalyst, the optimum ratio is 0.5. And in the case of rhodium-molybdenum catalyst, the optimum ratio is 0.13. This is a result of the characterization of these catalysts. Molar ratio, particle size from XRD, dispersion from the XRD, and seaward absorption. This is a difference between the dispersion minus seaward absorption, which means that the coverage ratio of molybdenum and rhenium on rhodium surfaces. The size and dispersion of rhodium metal particles were almost the same on these catalysts, almost the same. And the amount of seaward absorption decreased with increasing the additive amount. An important point is molar ratio below 0.13. The difference was almost the same as the molar ratio. This indicates that all the molybdenum or rhenium atoms suppress the seaward absorption. On the other hand, the ratio is above 0.13. These values are smaller than these values are smaller than molar ratio. This suggests that the part of molybdenum or rhenium don't suppress the seaward absorption. All the molybdenum or rhenium atoms suppress the seaward absorption at this molar ratio. This indicates that all the added molybdenum and rhenium atoms interact with rhodium metal surfaces. In particular, the catalyst with 0.13 ratio were characterized by EXAFS and compared. This is a result of molybdenum cage EXAFS analysis. At 0.13, the molybdenum oxygen and molybdenum rhodium or molybdenum bond was detected. Unfortunately, it is difficult to distinguish between the molybdenum and rhodium as a backscattering atom because atomic numbers of molybdenum and rhodium are similar. An important point is that the coordination number of molybdenum rhodium or molybdenum bond is as small as 3.0. This figure shows the results of the rhenium L3H EXAFS. At 0.13, rhenium oxygen and rhenium rhodium, rhenium bonds were detected. The presence of rhenium rhodium bond indicates that a direct interaction between the rhenium and rhodium. And the presence of rhenium bonds suggests that the formation of the rhenium OX clusters. This is, we make a model structure of these catalysts, considering from the EXAFS results. In the case of rhodium-molybdenum catalyst, the coordination number of this bond is equal to 3. Therefore, this suggests that the isolated molybdenum species adsorbed on the threefold follow site of rhodium-111 surface. On the other hand, in the case of rhenium, coordination number of rhenium-rhodium is 3.8. and coordination number of rhenium bond is about 2. This suggests that the rhenium X clusters are dissolved on the threefold follow site on rhodium-111 surface. You can see that the gray circle and white circle, gray represents the rhodium atoms, surface rhodium atom with adjoining molybdenum or rhenium. White circle represents the rhodium without adjoining rhenium. In the case of molybdenum, all the surface rhodium atoms are modified with isolated molybdenum species. Therefore, the optimum ratio is 0.13. On the other hand, the surface rhodium atom without the modification with rhenium X clusters, white circle, are present. Therefore, more added rhenium is needed. The optimum ratio is about 0.5. I would like to move on to the topic of iridium-rhenium catalyst. This figure shows the effect of rhenium amount. The conversion increased with increasing the molar ratio of rhenium to iridium. Optimum rhenium amount is much higher molar ratio compared to the case of the rhodium-rhenium and rhodium-molybdenum catalyst. According to the Zarnes analysis, balance of rhenium on iridium-rhenium is determined to be the plus 2.7, low valence rhenium. Although the details are not shown here, the balance of rhenium on rhodium-rhenium is determined to be the plus 2.3, low valence of rhenium, almost similar. This figure shows the XPS results. Rhenium is reduced, Rhenium is reduced from 7 plus to delta plus. Delta plus is between 0 and 4 plus, which supports Zarnes results. In the case of iridium, iridium is reduced from 4 plus to iridium 0 metallic state. This figure shows the results of the rhenium S-range exhaust. According to the curve-fitting analysis, the rhenium oxygen and rhenium iridium or rhenium bond was detected. Unfortunately, it is very difficult to distinguish between the rhenium and iridium as a backscattering atom. But an important point is the coordination number of this bond is rather high. This large coordination number suggests that the formation of rhenium X clusters. This slide shows the characterization results of iridium-rhenium silica catalyst. CO adsorption and particle size of iridium from XRD and dispersion from XRD. The difference between the dispersion and CO adsorption, which means the coverage ratio of rhenium X on iridium surfaces. Rhenium addition promotes the dispersion of iridium metal particles. The difference is the 0.36, which is much smaller than 1. 1 is the molar ratio. This suggests that the three-dimensional rhenium X clusters is formed on the iridium surface, which is also supported by large coordination number. This is a model structure of iridium-rhenium silica catalyst. This catalyst has iridium metal particles 2 nanometer covered with three-dimensional rhenium X clusters like this. This figure shows the relation between the selectivity and structure. Molybdenum on rhodium is monomer, and rhenium on rhodium is two-dimensional cluster. Rhenium on iridium is a three-dimensional cluster. Selectivity of hydrogenolysis is influenced by the modifier structure, such as monomer, two-dimensional, or three-dimensional clusters. We are thinking that the three-dimensional clusters are more favorable for higher selectivity. I would like to explain the reaction mechanism of glycerol and THFA hydrogenolysis. This figure shows the results of the kinetics of glycerol hydrogenolysis over iridium rhenium silica catalyst. This is a result of the effect of hydrogen pressure, and this is a result of effect of glycerol concentration. In this experiment, the molar ratio of reactant to catalyst is constant. Therefore, conversion is proportional to the reaction rate. From the effect of hydrogen pressure, first reaction order with respect to the hydrogen. First reaction order. And the effect of, from the effect of the glycerol concentration, zero reaction order with respect to glycerol above 20% glycerol concentration. This figure shows the reaction kinetics of the effect of concentration of the THFA. Reaction order with respect to the THFA on rhodium silica is 0.4, which suggests that a weak adsorption of THFA. On the other hand, reaction order with respect to the THFA on rhodium rhenium silica is about zero. This indicates that the strong adsorption of THFA, and this strong adsorption of THFA can be due to the interaction of CSO's group in the THFA with rhenium species. This is a result of the reaction kinetics in THFA hydrogenolysis effect of hydrogen pressure. In the case of rhodium silica, reaction order with respect to hydrogen pressure is 0.5, which indicates that the homolytic dissociation of the hydrogen. On the other hand, in the case of rhodium silica, the reaction order with respect to the hydrogen is fast. We interpreted this phenomenon is heterolytic dissociation of hydrogen. This is to summarize the kinetic results. Kinetics of hydrogenolysis of glycerol and THFA are very similar. Zero reaction order with respect to the glycerol and THFA. And the first reaction order with respect to hydrogen. Zero reaction order with the orders indicate that the strong adsorption of the glycerol and THFA, which can be due to the interaction of OH group with rhenium classes. Zero reaction order, not negative orders, also indicate that the adsorption of glycerol and THFA did not suppress the hydrogen adsorption. Hydrogen and glycerol THFA is non-competitive adsorption on the different adsorption sites. And the first reaction order with respect to the hydrogen suggests the heterolytic dissociation of the hydrogen to proton and hydride. Regarding the heterolytic activation of hydrogen, two kinds of reaction mechanism assumed, expected. First is a proton hydride mechanism by a cation reaction intermediate. Second is a hydride proton mechanism by anion reaction intermediate. We investigated the tendency of the product distribution of the ethers hydrogenolysis over this catalyst in order to clarify the reaction mechanism. We tested two kinds of reactants. In the case of rhodium silica, this catalyst catalyzed only the upper reaction route, red arrow, with very high selectivity. If the hydrogenolysis mechanism is proton hydride mechanism, proton attack to this molecule gives two kinds of secondary carbocations. In the case of this molecule, proton attack to these molecules, one primary and one secondary carbocation intermediate. We think that the energy difference between two carbocation intermediates is so small that very high selectivity is difficult to explain. Therefore, we are thinking that the hydride proton mechanism, the reaction can proceed by anion intermediate formed by the attack of hydride from the side of CH2 group. This direction is very important. This direction can cause high selectivity. This slide shows the reactivity tendency of various substrates. These substrates are reactive in the hydrogenolysis of the CO bond neighboring to COH2OH group. On the other hand, these molecules are inactive in hydrogenolysis of isolated CO bond and in the hydrogenolysis of inner glycols. Low reactivity of 2,3-propane diol indicates that the importance of the CH2 group, primary alcohol. This figure shows the results. This figure shows the reaction mechanism, including the iridium rhenium structure. Strong synergy between the iridium and rhenium suggests that the active site is interface between the iridium and rhenium X clusters. Rhenium X clusters adsorb the glycerol, and iridium metal activates hydrogen. And 1,3-propan diol is produced by the attack of hydride species on iridium metal to 1-glyceride formed on the rhenium X clusters. Reaction mechanism of the THF hydrogenolysis is also similar to the case of glycerol. CH2OH group is adsorbed on the rhenium X clusters to form alkoxide species. Hydrogen is activated on rhodium metal surface, and the hydride attack of CO bond neighboring to the CH2OH group. This figure shows the relation between the selectivity to 1,3-propan diol in the glycerol hydrogenolysis and the structure. Selectivity to 1,3-propan diol, very low, medium, and high. These are the 6-membered ring transition state to 1,3-propane diols. And these are the 7-membered ring transition state to 1,2-propane diols. Very low selectivity suggests that these are the comparable. In the case of medium, this one is favorable. High selectivity represents the very, this one is much more favorable. From this discussion, these rhenium atoms destabilize the 7-membered ring transition state. And another important point, it should be noted that the 7-membered ring transition state is related to the hydrogenolysis of 1,3-propane diol to 1-propanol. And this scheme shows the indirect route of the THFA to 1,5-pentane diol. 3-step process was catalyzed by acid and metal. Dihydropyran is intermediate of the indirect route. When dihydropyran was used as a reactant on this catalyst, significant amount of tetrahydropyran was detected. On the other hand, when THFA was used as a reactant, tetrahydropyran was not detected at all. No detection of the tetrahydropyran strongly suggests that the direct reaction route in the hydrogenolysis using iridium rhenium, rhodium rhenium, and rhodium molybdenum catalyst. But I'm sure that the rhodium rhenium X silica has acid sites. This is a result of the ammonia TPD. But the acid strength is not so high. Therefore, the role of acid on rhenium X catalyst is very weak. This is a paper reported by the Professor Domestic. He reported that the direct hydrogenolysis assisted by acidity of rhenium on rhodium. Hydride transfer creates a stable oxocarbenium ion after the attack of proton. Hydride transfer. Although the reaction mechanism, proposed reaction mechanism are different, but the important point is he also insisted that direct hydrogenolysis. Finally, I would like to summarize my talk. Iridium rhenium silica catalysts are effective for the glycerol hydrogenolysis 2,1,3-propane diols, and rhodium rhenium and rhodium molybdenum catalysts are effective for the THFA hydrogenolysis 2,1,5-pentane diol. The catalyst structure of rhodium molybdenum species is rhodium molybdenum catalyst is isolated low valence molybdenum species on the rhodium metal particles like this. Catalyst structure of rhodium rhenium catalyst is two-dimensional clusters of low valence of rhenium species on rhodium metal surfaces. Catalyst structure of iridium rhenium or X-silica catalyst is three-dimensional clusters of low valence rhenium species on iridium metal particles. Strong synergy between the metal, rhodium or iridium, and modified oxides, rhenium or molybdenum, indicate that the active site is the interface. The reaction proceeds by the attack of active hydride species on metal to alkoxide formed on the rhenium X clusters. And the radioselectivity of the hydrogenolysis can influence by the structure of the modified oxide, monomer, two-dimensional or three-dimensional clusters on the metal surface. Conventional hydrogenolysis is multi-step reaction. In contrast, iridium rhenium catalyst, rhodium rhenium, and rhodium molybdenum catalyst catalyze a direct, single-step hydrogenolysis of the glycerol and THFA. In addition, although we did not show the details, but these catalysts showed very low activity in the degradation reaction, CC cracking reaction. Considering from these results, direct hydrogenolysis will enable the selective conversion of polyols and ethers with much more complex structure. Finally, I would like to express my thanks to the three professors, Professor Iwasawa, Professor Fujimoto, and Professor Kunimori. Three professors who taught me how to live in the research field. And I also thanks to my colleague and collaborating researchers and the funding program and various Japanese companies. Thank you very much for your attention.